20 seconds. T-minus 15 seconds. T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, fire. T plus 5 seconds. T plus 10 seconds. T plus 20 seconds. T plus 30 seconds. T plus 40 seconds. T plus 50 seconds. T plus 60 seconds. T plus 70 seconds. T plus 80 seconds.
Central Support Systems Operator, enabled with low CO2 and French door controls. Enabled.
T plus 90 seconds.
Open the accumulator enable valve. Accumulator is enabled.
T plus 100 seconds. T plus 105 seconds.
Activate after-rouge. Activated.
T plus 10 seconds, 110 seconds.
Activate forward rouge. Activated.
T plus 120 seconds.
Activate head and CO2.
Activate.
Activate quench tool command forward and aft CO2.
Activate. T plus 170 seconds. High-speed data operator, stop recording.
High-speed recording is complete.
Roger. Low-speed data operator, stop recording.
All right, so that what you were seeing there was, of course, that was the test firing of the solid booster that's being used for NASA's Artemis mission, which is due to launch on the 29th of August, and it was being taken out to the launch site today. So they put it on one of these giant crawlers, you know, like they had with the Apollo Saturn V's, to actually take it out to the launch site. So it's probably at the launch site at the moment, and then whether or not they wait until the 29th of August or whether they actually go early remains to be seen. I suppose it depends on a lot of things, such as the weather. Now, that booster that they were testing there is actually more powerful than the Saturn V booster. So even as of today, the most powerful rocket ever built is the Saturn V. But when Artemis goes up, assuming it does go up in August, it will be the first one where they try it will be 10% more powerful than the Saturn V, and then the second one that they try, which will be the manned mission, will be about 50% more powerful. So this initial one that is going to be launched probably in the next few days to a couple of weeks will be unmanned, nobody on board. Obviously they won't get any gremlins out before the second launch is going to have astronauts on board. So Artemis is meant to be sending a woman to the moon, and also, to use the American term, a person of colour. Now, I don't know who they've actually chosen for those two, but that's like the signature of it. So the Americans are going to put like a base around the moon, and also a base actually on the surface as well, so like a gateway in orbit around the moon. So that's going to go very, very soon. Now, the other thing that you might have actually heard during the month was Earth has actually had its shortest day on record on, in fact, June 29th, I think it was, which means Earth is now spinning faster, whereas historically Earth has actually been slowing down with time. And in the same way as we have to insert a leap day, every February 29 every 4th year, with rules against that. Every 100 years, 400 years and so forth. Because the rotation of the Earth itself is slowing down, or traditionally we've had to insert an extra leap second every couple of years. And for example here you see in June 2015 you actually had 60 seconds in that particular minute before it turned over to 00. So in other words, they inserted one extra second. And the purpose of that is to keep atomic time in sync with what the Earth is actually facing in space. So if you're looking at a distant radio source, you time it exactly to when you're pointing at it again, exactly the 1 year later. So what they found is it's about 1.5 milliseconds, so a small amount, but obviously things are going on deep within the Earth, in the liquid metal parts of the core, moving around, that has actually caused us to speed up. So it's caused a few scratching of the heads. The slowing down was thought to be due to the moon causing tidal drag on the Earth. So as the moon is slowly moving away, it's causing us to rotate very, very slightly slower. But this is a speed up, and it may very well be that in the next few years they have to insert a negative leap second. So in other words, have a minute that only has 58 seconds, and the 59th disappears that particular year, to try and correct us back. So very much an ongoing thing. Now, of course, when you have very powerful rockets blasting like that horizontally, it does make you wonder if they're in the right direction. Would they actually cause the Earth to slightly spin up or spin down a little bit? Particularly if you have enough of them. I wonder whether they take that into account. Okay, moving to the next image over here. That one was done by Australia's new most powerful supercomputer in Western Australia, and that's part of the prototype of the square kilometre array. So it's a radio telescope took that image, and absolutely exabytes worth of data came in, and that supercomputer worked on it for 24 hours to actually come up with that image. And I think even this one, we're barely in the top 10 worldwide in terms of supercomputer power that it can do, but it's certainly much bigger than what we have anywhere else. And of course this month as well, a very, very similar image is that one that was doing the rounds, and that may have been doing the rounds years ago, or probably surface for many years to come. A bit like Mars appearing very large in the night sky every August or every 2nd of August. And that one was circulated by an astronomer, a French astronomer, as apparently being a James Webb Space Telescope image of Proxima Centauri. But for those of you that know, that's actually a cross-section of a Spanish sausage, how do they pronounce it? A choriza. So they pronounce the Z as like a TH sound, choriza. So as you can see, that's not Proxima Centauri. You're seeing detail on the surface of the star. It's actually a sausage. Hence the Spanish connection.
Someone said it's a baby.
During the month, we also had bits of debris coming in from space. We had the Chinese Long March rocket, which is 25 tonnes. So, in other words, it's the mass of a very large truck coming in. And the thing with that one is it was a completely uncontrolled re-entry. So, in other words, they used all the fuel up, and it just came in wherever it was going to come in. And that was the worry about it. And then the second worry was the Chinese actually refused to share the trajectory of it with anyone else, so you couldn't even plan or prepare your population if it was coming over you. It was a case of it would come down and drop on you, and the first you'd know about it was when it actually hit and caused some damage. So it was photographed there in the sea between Borneo and Philippines by fishermen coming over, so you see the thing breaking up into pieces, and the bits that survived would have landed in the ocean. Down here on the left here is during the month also the University of Tasmania was gifted a new mount for their Green Hill Observatory, which is a few kilometres outside of Hobart, and this is going to be used for tracking space junk. So it's a 1.3 metre telescope in there, and with this new mount it can slew at 20 degrees per second. So 20 degrees is probably about that, and it will follow things in fairly low Earth orbit if needed that are going very, very quickly as well. So that moves at a fair pace indeed. And other space junk that's arriving, so on the 9th of July over the snowy mountains, more pieces came in, and you'll recognise if you're an aficionado of sci-fi, the opening scene to 2001 A Space Odyssey. Interestingly, in Arthur C. Clarke's original original book, it wasn't called A Space Odyssey, it was called The Sentinel, and it wasn't like a rectangular prison there, it was a tetrahedron in the originals, but because the tetrahedron was too difficult to build for the set of the movie, it was proposed to actually make it into a 1:4:9 ratio, and the prototype that they actually built to get the director's approval was made of perspex, but the problem was it looked too much like glass, so they then required it to be painted matte black, and that gave it a more sinister and mysterious appearance in the movie, and that has stuck ever since. Now the one that actually came down a little bit north of the Victorian border there, and Brad Tucker from the Australian National University went out to it, and I'll show his posting about it, which will go for a couple of minutes.
Hey, it's Dr. Brad, and I've just returned from a trip out to a farm in rural New South Wales in a town called Dalgety, where it is believed that a farmer has found a piece of space junk from a SpaceX Crew 1 trunk. Where we've ended up is super remote. There's nothing around it. In fact, just the paddock itself is hundreds of acres in size, so it's easy to not see this piece of junk from a distance. So I get lots of reports of space junk, and it's usually easy to rule out. What made this one special was the SpaceX Crew 1 trunk was a catalogued object, and it was catalogued known to be going over New South Wales in Australia and re-entering around 7 a.m., 7:05 a.m. on Saturday, 9 July. Now, on that time, people heard and saw it. So people heard the sonic boom of it re-entering the Earth's atmosphere, and people saw the bright light and bits breaking off of the object fragmenting as intended. So we had a piece of junk that was catalogued over the area, both seen and heard around the right time. What day did you find it?
Monday.
Okay.
So this is a while after this thing's happened.
It did. Yeah, so it happened on Saturday the 9th.
Yeah, but it's direct. Once we get down into the next gate, you'll be able to, well, I can see it because I know where it is. Yeah, that's it. Yeah.
Goodness.
Yeah, that's pretty cool. And yeah, you just see it sticking out of the ground.
You couldn't see from here to that bush because of fog, so we wouldn't have seen it. But if I'd have seen that from here, I wouldn't have took one bit of notice. I'd have thought, oh, that's an old burnt tree.
Yeah, exactly.
You know, like it wouldn't even tweak to me that it'd be something like that.
Well, as you said, you know, there's not a crater, there's not, if it was a big hole in skirt, yeah.
About a month ago, and I found it on Monday. It was about 10 o'clock over there. on the side of the hill.
It looks like a, what do you think it looks like if it wasn't?
Well, when I first seen it, I thought it was a lucerne mower.
Also, it looks like a dead tree.
Yeah, well it does now that I know it's there, but when the first thing I looked when it was foggy, that's what I thought what it was.
Come around.
Yeah, he's coming now, but he must have dropped that here before because that wasn't here.
So this is the piece that landed on Jock. Oh, yeah, okay. And then you said so that's kind of. Oh, here he is.
Here he is. Yeah, so this is the bit coming here.
So as you get up close, you can kind of see really subtle detail in all the features. You can see some of the scarring already on this panel. This is due to the heat re-entry. You can start to see cabling, so kind of this is a carbon mesh, and what it's doing is to insulate both around any cabling and any wires. You know, keeping in mind this has to withstand intense heat. Now, firstly, some people think this stuff is radioactive, and it's not. Yes, there is radiation in space. Things don't come back radioactive all of a sudden. And it's also been out in the weather, the rain, the wind for a couple of weeks, so any loose, potentially harmful bits may have blown and washed off. And so we think this is a fin. This is a part of the fin of the trunk that has now speared itself into the ground. And it's about 3 meters tall. We think it weighs about 20 to 30 kilograms. Obviously, we haven't dug it out of the ground. So here we have some clear paneling that is designed for insulation and heat resistance. You can see part of it's melted, but the crack inside shows what it's like. This is triangular in shape, so we're looking at kind of one of the other pieces, some of the bolting and the manufacturing, and you can kind of see the angle that it's wedged at and some of the insulation. Experts have checked out to make sure all the material is safe and isn't a danger to anyone. This big piece is the one that wedged itself onto Mick's farm, and Jock brought his piece over from the farm next door. And as you said, yeah, the serial number is kind of helpful. Yeah, this has been super exciting to see this all up close. Look, I've never seen a piece of space junk fall like this. This is an extremely rare event, and it was super exciting to be out there to help verify and confirm it.
So, given that he said it's only 20 kilos, it's done pretty well to embed itself in that ground.
The dogs were pretty nonchalant about it.
Yes. So I think they ended up retrieving about 3 or 4 pieces from neighbouring farms as well, but I think that was the largest piece that they actually had there. Okay, so...
does that belong to whoever's property for right now?
I don't know. In that particular case, it probably does actually in Australia. Yeah. Because of course they had when Skylab came down over Central Australia many years ago. That was a similar thing, wasn't it? That large pieces came down, and some of it landed in the Woomera prohibited zone, so that was obviously Commonwealth property. But if it had landed on private property, yeah, who actually then owns it? Okay, so tonight I'll show a video about space junk by Jonathan McDowell. He actually had a bit of a scathing comment actually online about the Chinese re-entry uncontrolled. He's got quite a bit of expertise in this area, and he's consulted by the European Space Agency and NASA for how he keeps up to date with everything that's launched every week, and he publishes a weekly report of everything that's been launched and tells you all the details of the launch, whether or not they're secret ones or not. So he obviously has his sources able to work out these sort of things. Then we'll have Sky for the month, and then afterwards we'll look at where is the edge of space, so where does space begin and why is it there, and then how to actually cut a cake. So there's 2 videos there on how to cut the cake, and we'll see how well Nerida has done cutting the cake. There are two parts to this one. One is how to cut the cake when you want some the next day, and the other one is how to cut the cake when you want to give a nice fair portion to however many people that you have. So, recent events in society, we started to obviously pick up in terms of number of public nights, and fortunately the night Catherine was on, the last public night in August, was nice and clear outside, so we had a pretty good turnout, given how cool it is. Then the South Frankston Joeys was a couple of days later, and they had no cloud in the sky, and they had a really great time as well. Mount Erin unfortunately was 100% clouded, so we had plenty of members turn up, but unfortunately the clouds weren't kind to them, which is a bit unfortunate because they've been trying to get to us for nearly 3 years now, and the previous 2 years had to be called off due to the lockdowns at just the wrong time. They're a bit unfortunate, but we'll probably see them next year. The general Skag Night, Scout Cubs and Guides, saw the place full to our sort of COVID capacity. But unfortunately 100% clouded as well, and Catherine and I did the talk on that one. And then Eden White kicked off the cosmology discussion group, which was last Saturday, and by all accounts I hear quite a number turned up for that one, given that it was shocking weather here at the Briars as well. And the comments I've been seeing online is people have really enjoyed it. So those that have posted to eScorpius, and some that didn't actually post to the general ones, but were kind enough to actually copy me in on it as well, so I could see, and all of them were really happy with how it went. So I think that could very well be a good success story, and hopefully it will keep going, and the interest will remain. Coming up soon, we'll have used a smaller font for this one, so the next month is starting to look a little bit crowded. So this Friday we have the National Science Week viewing night for the public here at the Briars, where Trevor will be talking on meteorites and bringing along his meteorites. Chances are we'll probably only end up with maybe 40-50 people, given the time to go until then. But we can certainly go up to 70 if we wish. Working bee this Saturday as well, as usual, at 4 o'clock. Committee meeting next week, and then there's a bit of a gap until around the end of the month, when we start going into some of more scouts and school nights. So we've got Strathcona again down at Merrick's Lodge. We've done them for quite a few years now in a row. And several others down there as well, including Hartdale Secondary, which is also a regular one as well, and we usually get a lot of people for that. So they're a very big school to have over 200 Year 7s alone there, so very large secondary school. And then astrophotography workshop towards middle of September, so that's about half booked at the moment, so there's still space there for people that are interested and able to actually get to it on a Saturday. Right, so tonight's feature is this one, Dr. McDowell. This talk, I actually looked around quite a bit for talks on space junk, public talks, and there were recent ones, but they weren't particularly good. They were talking about current research interests of, for example, firing nets around satellites to try and snare them, and then trying to drag them back down into orbit and force them to come back down. But they didn't go into what is the actual problem that they're trying to solve, and the history and the background of it. Whereas this one, this particular talk is a couple of years old now, but it does actually go into some of the details, so that's why I've actually preferred this one. Those that are interested in his weekly report, which incidentally did include the 3 Australian rockets that went up as well. They include suborbital ones like that don't actually go and stay up into orbit. He does this as a labour of love, not as part of his day job, but part of his nighttime enjoyment. He's also IT responsible for the data software of the Chandra X-ray telescope as well, so he has quite a diverse background. Now this talk goes for about an hour, and then after that we'll go to sky for the month, and then we'll have a break. Given the number of people here as well, will be pretty informal anyway. So if you feel like getting up and having a cuppa or grabbing a bit of cake before it gets properly cut, feel free to do so.
So it's now 60 years since the launch of the first artificial satellite of the Earth, Poszczeszczy Sputnik 1, the simplest satellite #1 from Baikonur in Kazakhstan. This is a picture of the launch, and this is the 83-kilogram satellite that it put into orbit. But you may not know, probably most of you have heard of Sputnik, yes, you may not know that actually Sputnik is the second object in the catalog of satellites that we keep. The first object, catalog #1, was this rocket stage that put it into orbit. Because when you launch a satellite with a rocket, the rocket stage has to go into orbit to get the satellite into orbit. And so the very first orbital space launch had a big piece of space junk that re-entered after a few months, but still. And so what you do when you're going into space is you launch a rocket up through the atmosphere, get out of the atmosphere so there's no friction, and then you go sideways for a few minutes, building up speed to the magical orbital speed of about 17,000 miles an hour. And that's how you can stay in orbit. I'll say more about that later on. And so what you do is then your rocket switches off, you're at the orbital speed, you just fall around the Earth, and now you separate the satellite, but the rocket's still in orbit. And so that's one source of orbital debris, which is the technical term for what most people call space junk. So why is that a problem? So I want to introduce you to my friend Iridium 33. It was a half-ton communication satellite launched in 1997, and it was zooming around the Earth quite happily for 12 years, working, relaying cell phone communications. And one Tuesday it met this guy, Cosmos 2251, which had been a Soviet Ministry of Defense communications satellite, but for many years it had been inert, it had been switched off, and when you switch a satellite off, it doesn't just come down, it stays in orbit right where it was. And so it was orbiting the Earth as a piece of space junk. And 480 miles over the Arctic, Iridium was orbiting the Earth like this, pole to pole, and Cosmos was orbiting like this, pole to pole. And so they come in, the relative velocity at which they said hello to each other was 26,000 miles an hour. Now, yes, ouch is the correct analysis here. And let's say, but you know, ouch would be, I think, imagine a 1-ton truck hitting you at 100 miles an hour. That would be ouch. But as many of you may remember from high school, a half mv squared kinetic energy, if you go 10 times faster, there is 100 times more kinetic energy. This is why you should obey the speed limit, Boston drivers. And so this, compared to the 1-ton truck at 100 miles an hour, this had 54,000 times as much energy. So that's a big ouch. And so a few hours later, what you see is this string of pieces of debris along the individual orbits. What happens in a hypersonic collision like this, it turns out, and the Department of Defense did an experiment to determine this, you smash into each other at 26,000 miles an hour, a hypersonic shockwave goes through both vehicles, reduces them to confetti, and the clouds of confetti pass through one another without really interacting much. And so they end up pretty much on the same orbits that the original satellites were on. I remember to turn off my phone. And so pretty soon, and then various complicated effects mean that these sort of trails of pieces of debris spread out into a shell around the Earth, so that they're there for any other satellite to hit them. Currently, the radars on Earth can track things that are maybe a few inches across, And we have about 2,200 pieces from this collision in the catalogue. Now, some of them are re-entered. About 700 have re-entered, but that's still well over 1,000 pieces from this 2009 collision that are still in orbit. So that's why space debris is a problem. Even small pieces are not good. The smallest things we catalogue are typically a couple of pounds, typically a few inches across, and that's like, if that hits you, that's like a 1-ton truck at only 1,000 miles an hour. So it's still like being hit by a missile. And here's a French Defense Ministry satellite that got its antenna taken out by a piece of debris back in 1996. So these collisions happen, not too often. The really big ones maybe are like the one every 10 years point right now. But here's the problem. We're launching more and more satellites. And this is another of these squared problems, that if you have 10 times as many satellites, you have 100 times as many collisions. And so if it's at one every 10 years now, if you have 10 times as many satellites, it's going to be one a month. So there's another problem with space debris that you might worry about, which is that it might crash to Earth and cause lots of damage. There's been some media press about that recently. But the thing is, when you enter the atmosphere, so you're orbiting the Earth, and if the Earth didn't have an atmosphere, you just orbit forever and ever, falling around the Earth, just like the Moon does. It's far enough away it doesn't feel the atmosphere. But if you're even 500 miles up, 300 miles up, there's just a little bit of air. Not enough to breathe, millions of times less than what's in this room. But if you're going at 17,000 miles an hour, that still makes quite a headwind. And it slows you down. Imagine sticking your head out the car window on the freeway, right? Now imagine doing that if the wind is 17,000 miles an hour. And so it slows you down, and you spiral in closer and closer to the Earth. And the closer you get, the denser the atmosphere is. And at a certain point, it gets so dense that you're really heating up because of the atmosphere. The energy of the molecules hitting you is making you hot. You melt, you break apart. And most of the space junk that comes down just melts up completely. But the big chunky ones may be so big that they re-enter so quickly that it hasn't had time to melt all the way through. They have dense materials. A lot of satellites are made mostly of aluminium. Or aluminum to people here, and so they'll that has low melting point. But there are pieces like rocket engines and so on that are made of sterner stuff that can get all the way to the ground. The biggest ever that came down was the 75-ton Skylab space station in 1979 that scattered pieces of itself all over the Australian desert. And nowadays the practice is, if you have a big thing like that, you have a rocket engine on it, and when you're done with it, you deliberately bring it down under control in this area of the South Pacific called the Spacecraft Graveyard, which is, there's a piece like southeast of New Zealand which isn't on the way to anywhere, unless you're a penguin, and so there's no like shipping lanes and air lanes, and so you can just burn it up over there without worrying that you're going to hurt anybody. So that's what the big ones mostly do. But there have been a few incidents. The most notorious of which was the Soviet Navy satellite Cosmos 954 in 1978, which had a big radar to track American Navy shipping. And that big radar needed a lot of electricity, so they put a nuclear reactor on it. They had a whole series of these things. And the rocket engine stopped working, and it re-entered and spread radioactive debris all over Great Slave Lake in Canada. And you see here pieces of spacecraft metal melting holes in the ice because of their radioactivity. So this was really not good. And occasionally you get fuel tanks of rocket stages that they're big empty tanks, and they get banged up a bit in re-entry, but they kind of float down. And so here's one in Texas from a Delta rocket, very similar design of one in South Africa. Here's a fuel tank from a Russian satellite in Brazil. And so the satellite, breaks up into little pieces, but a few get down. But no one's actually been hurt by re-entering space debris, except arguably for Lottie Williams here of Tulsa, holding the piece of space debris that floated down and hit her on the shoulder. She wasn't hurt because terminal velocity was low, and this was kind of just really floating down. But she's the only person we know of who's actually been hit by space junk. So the biggest reentries to come down, I said Skylab, almost 80 tons, came down in 1979. The rocket stage that put Skylab in orbit also came down at 775. That was 49 tons. And the Salyut 7 space station with an attached module, 39 tons, came down in 91. Those were the big ones that came down, not in the spacecraft graveyard, not under control. Those were bad. We don't want those. There's been a lot of press lately about a Chinese space lab called Tiangong-1, which is re-entering probably around January. It's only about 8 tons. It'll mostly burn up. Maybe a little will reach the ground, but we get something like that once every few years. So I think there's a lot of overexcitement about it. So that's the two things that can go wrong. Space junk can hit your satellite, or it can fall on your head. So how big a problem is this? How much junk is there? So this isn't the junk. This is the working, useful satellites versus time from 1960 to the present day. And if you think about the height of the space age, you think of the 1960s maybe, but there were only, a few dozen usually active satellites working at a time back then. Now there's almost 2,000. See how steep this curve is? We're using space a lot more than we used to, and the trend is straight up. What are we doing up there? These are the main kinds of artificial satellite that we have going around the Earth. Communications satellites, maybe 6 tons, usually sitting in geostationary orbit 22,000 miles over the equator. Earth imaging satellites, maybe for Google Earth, maybe for a 3-letter agency that's spying on somebody. Those are typically a few hundred miles up going over the poles in what's called low Earth orbit. There's also a category of signals intelligence, which is exclusively for the military, listening in to radars, enemy radars, and maybe your phone calls. There's a lot of little tiny technology satellites. I'll talk about those a little later. And of course, half of you wouldn't be able to find this place today without the GPS satellites. And then there are some science satellites like Chandra here that Martin and I both work on and is continuing to return exciting science. And also spaceships with astronauts on board, they're satellites too. And so I did sort of the breakdown of what they're used for, and by number of satellites. The biggest things are either communications or imaging, and the technology satellites are pretty common too. The trick is that the technology satellites are mostly really tiny, whereas these ones are big. So most of the action is in imaging and communications, and you'll see that science is really a small part of the pie. And the people who's doing all this, I've shown here the people who own satellites and the people who build satellites, and the answer is pretty much the same, that the big players in space are the US, Russia, Europe, and China, with India and Japan kind of the next tier down. And the division is between civilian, defense, and commercial about equally. And non-profit is coming up. This is university satellites mostly. That's number of satellites. If you look at maybe a better proxy for how much this all costs is the weight, the mass of the satellite. And so I divided it up that way. And by mass, the human spaceflight, this color on the left, is the most, because this is all the stuff launched since 2010, and that included some space shuttles and some space station modules. The space shuttles are 100 tons each, whereas these the little technology satellites here are often a couple of pounds, and so they don't show up at all when you do it by weight. But if you ignore the human spaceflight, which is a lot of the money, it's sort of equally divided in effort between civilian, military, and commercial now. And so most satellites are either in low orbit a few hundred miles above the Earth, or in this geostationary ring at 23,000 miles. So the geostationary ring, right, is that the higher you orbit, the longer it takes you to go round. If you're orbiting just above the Earth, you go round the Earth in 90 minutes. If you're at the distance of the Moon, it takes you a month. Not coincidentally. And in between, it takes intermediate amounts. So somewhere in between, there's a height at which it takes you exactly a day. And if you're in an orbit that takes exactly a day to go around the Earth, and the Earth is also spinning once a day, you keep pace with somewhere on the ground that beneath you. And so it seems to someone on the ground that the satellite isn't moving, and that's why if you have a direct TV dish, you don't have to keep moving it. So the geostationary orbit is very popular for that reason, which is why there's so many satellites there. So, and just to re-emphasize, some of these satellites are really tiny. So starting in 2003, they introduced the CubeSat, which is 4 inches, 2 pounds. There's a triple version that's very popular, that's like a foot-long hot dog, basically. You know, in 2000, they launched a few of those a year. This is how many of these CubeSat launches per year, until about 2013, and suddenly they started launching 100 a year. They finally got the electronics and everything miniaturized enough that you could do something useful with one of these tiny satellites instead of just, you know, have students build it and have a webcam and go, oh, we built a satellite. And so now companies are building these satellites, and they're going up at the rate of 100 a year, and that's really, really changing the sort of demographics of the satellite population to have all of these small satellites orbiting the Earth. At the other extreme, this is the biggest artificial Earth satellite. This is the International Space Station, 420 tons. So if you think of one of these 4-pound, 1-kilogram CubeSats, this is 420,000 times, it's 500,000 of the CubeSats to make one of these. So a lot of the weight is in this one thing. But now I showed you that curve of how going up really quickly the number of active satellites. I've replotted it here in red. See, 2,000 number of active satellites going up. But these other colors are all the different flavors of space junk that go along with that. And so you can see that most of what's up there is space junk. So we have in black dead satellites, things that used to work but now are just falling around the Earth inert. Rocket stages, because like I told you, you launch the satellite with a rocket stage. This is sort of what I think of as general littering. If you have a lens cap that you eject, if you have 2 satellites and there's a little widget that separates the 2 that you throw off, anything else that you throw away that isn't in the other categories. And then this big green tranche is the other kind of debris, which is generally explosions of one kind or another, and we'll get into that in a minute. You see there's a lot of that. This is the shrapnel. And then in particular, you'll see that in 2007, there's a huge jump in the amount. This black stuff suddenly appears. That's from a single incident. That's from the Chinese military's anti-satellite test in 2007. And so they exploded this satellite. They did it in just the worst part of space. They generated huge amounts of space debris, and we'll see that later. And then the cyan, the light blue at the top, is another jump in 2009, and that's that collision that I showed you at the beginning, the Iridium satellite that hit the Russian satellite. And so just 2 incidents are responsible for a huge amount of the space junk that's currently up there. This is the same thing but by weight, to say that there's currently almost 9,000 tons of stuff in orbit, and almost 80% of that is junk. And so the worry is that as the amount of junk is increasing rapidly, we get this n-squared problem, 10 times as many satellites, 100 times as many collisions. And we could enter a chain reaction that's known as the Kessler syndrome, where you take all the satellites in space and they all hit each other rapidly, and you end up, instead of having a space program, you end up with Saturn's rings made of aluminum. And you're unable to use outer space for the next 100 years or something. So we really would like to avoid that. And so at the end of the talk, I'm going to talk about some ways in which we're trying to improve things so that we might still be able to use space and not completely mess it up. But first, we're going to do a little digression. Namely, we're going to just talk a little bit about what it means to be in orbit and what kinds of orbits there are. So I find out that not everybody, some of you already know this, so bear with me. There's a very big difference between being in space and being in orbit. So suppose I just go up into space 200 miles, switch my rocket engine off. What happens? I'm going to fall right back down. And so that's why when I launch the satellite, instead I also make sure I'm going 17,000 miles an hour sideways. And then in 1 second, I'll just, by high school math, you can do like in 1 second, you fall about 30 feet under gravity. But if you're going sideways that fast, at the same time, you've gone sideways 5 miles. And in that 5 miles, because the Earth is round, everyone's with me on that, right? No flat earthers. The Earth will curve away from you by 30 feet. And so you've fallen 30 feet, but you haven't gotten any closer to the Earth. And so you can repeat this trick to fall all the way around the Earth without using any fuel. So if you extend that, after almost half an hour, you've fallen 4,000 miles, and you would be in the middle of the Earth, but you've gone sideways 4,000 miles too, so you missed the Earth entirely. And this is where the really neat part of the trick comes in. So you had this sideways speed that you used to miss the Earth, but you're still picking up speed from gravity as you fall. But now you're over here, the downward speed that you got from gravity, which was a falling speed, is now a sideways speed, because the Earth isn't over here anymore, it's over here. And so you've turned the gravity, the falling speed, into a new sideways speed. And so gravity's now pulling you this way, but your old gravity speed is making you, helping you miss. And so then I would just turn your heads 90 degrees and repeat what I just said. And you can just fall all the way around without using up any energy. So that's what orbit is. It's as Douglas Adams says, the secret to flying is to throw yourself at the ground and miss. and that's as good a description as I can give of what's being in orbit. So for those of you who are complaining about no math in this talk, just for a moment, I'm just sort of throwing up, it just comes very simply from Newton's law of gravity, from the Kepler speed that you have to be at, is 17,000 miles an hour, and then you get Kepler's third law, which tells you the higher you are, the longer it is to take to go around the Earth. But you don't care about that. So what paths can you take? And one of the other really important parameters that I want to talk about is what we call the inclination. And the inclination is just, are you going round the equator? That's a 0 degree inclination. Are you going over the North Pole, South Pole, North Pole, South Pole? that's a 90-degree inclination. And something in between, like the ISS, it's at 51 degrees. What that means is it goes as far north as 51 degrees north, comes round, goes as far south as 51 degrees south, and up again. And the trick here is that what you're not allowed to do is the yellow curve. You're not allowed to go in a circle around a line of latitude, right? The gravity says that your orbit, the circle of your orbit, has to have the center of the Earth at the middle of it. You can tilt it, but you can't just move it up and down. The other trick is that the Earth rotates, and once a day, and it does so if you're sitting on the equator about 1,000 miles an hour. So if you launch from the equator, you get a free boost of 1,000 miles an hour. And if you're at the poles, it doesn't work, right? Because you're not going anywhere if you're at the North Pole. But even at the latitude of Florida, Cape Canaveral, to take a random example, you're still getting 900 miles an hour free speed. So you're going to launch east to take advantage of that free speed, and not west, where you'd have to add an extra 1,000 miles an hour to get the same satellite into orbit. And so we launch to the east and get this to this critical speed to get into orbit. So what I'm showing here is where all the satellites are, and along here I have. This is sort of a log scale from just a few hundred, I'm sorry, it's in kilometers, 100 kilometers above the Earth. So a few hundred miles above the Earth is where most of the stuff is. And then there's kind of a gap. And then there's this spike here, which is the magic geostationary height where it takes 24 hours to get round. And so in green are the satellites that are working, in red are the satellites that have died, and in black is the rest of the junk. And so roughly speaking, the satellites and the junk are in the same place, as you might expect, and they're mostly either in LEO, low Earth orbit of a few hundred miles up, or in geostationary orbit 22,000 miles up, and then there's the GPS satellites and a few others that are kind of in between. So let's up the ante, because that was an easy graph. So now we're doing something slightly more complicated. This is the same along the bottom is the height, but now I'm doing inclination. So at the bottom of the plot are all the things that are going eastwards, like I said, is the sensible thing to do. In the middle of the plot are the things that are going over the poles, 90-degree inclination. And at the top of the plot are the things that are going the wrong way round, to the west. And you'll notice that the top of the plot's pretty empty, because most countries are pretty sensible, and they launch to the east to take advantage of the free spin of the Earth. And most of the eastward stuff, the geosatellites are all over the equator, which they have to be, and the satellites that look at the Earth, particularly like this SSO area here, which stands for Sun Synchronous Orbit, which is another special magic orbit that's unfortunately a bit more complicated to explain, so I'm going to pass over that for now. And so you'll see that there's a lot of satellites here, a lot of satellites here, and then there's just one or two going the wrong way around. I just made this today. I can't think why I didn't think of doing this before. This is who owns that junk. So blue is America, red is Russia, green is China, and pink here is Europe. And so you'll see that there's sort of stripes on the inclination, because if you launch due east from a rocket launch site at 48 degrees north, then you go into an orbit with a 48-degree inclination. And so these stripes basically are different launch sites. And the Europeans have one in South America near the equator, and the Russians have ones in the far north, and there's actually the Cape Canaveral doesn't really show up very much in this particular plot. You'll also notice the green stuff up here, right, the Chinese debris, right in the area where all the Earth imaging satellites want to be, the Sun Synchronous Orbit. That's why the Chinese anti-satellite test in 2007 was so bad. It's right in the popular place. Just show you, zoom in on part of that plot. This is the geostationary orbit. All of the operating geostationary satellites in green, that's like 1 mile wide. The magic height at which you have to be geostationary has to be very accurate. And then when they retire them, the red crosses show all the dead satellites that have been moved away from the magic height with their last few gallons of fuel. And this is the area of the plot, zooming in, that shows the sun-synchronous, the polar orbiting Earth imaging satellites, which this lovely equation shows the purple line is where satellites would like to be. And you'll see that all of the green satellites, all of the operating satellites are really near this line. There's none over here, there's none over there. So that this equation, simple equation, really does predict where the satellites are going to be. And then all this black stuff is the anti-satellite debris that's really messing up that part of space. So that's not good. Let's talk a bit about the different kinds of space junk we have. And really, I divide it into two different kinds that I call deliberate littering and accidents. Although not all the accidents are actually accidents. So the deliberate littering, as I've talked about already, dead satellites, rocket stages that you've just left up there, and the jettisoned bits and pieces that you've thrown off. Accidents include, if you have a rocket stage up there, if you go to, there's usually about, some amount of fuel left over at the end of the launch. Maybe a ton of fuel, something like that. And if you go to the grocery store, right, you don't fill your car with just enough petrol to get there and run out when you get back. You always have a little left over. Maybe the engine will run a little hot, so you have to have some spare. So at the end of the satellite launch, you have some spare fuel and some spare oxidizer. Rocket fuel has two pieces to it. And you have maybe a rubber gasket keeping them nice and safe and separate, which 10 years later erodes. And suddenly you don't have a rocket stage, you have several hundred pieces of space debris. We have batteries, have kind of the same problem. There are the accidental collisions that I talked about, deliberate collisions, self-destruct, and breaking up when you get too close to the atmosphere. And so when you sort of census this, when you count up all this stuff, as you see, I have too much spare time on my hands. Since Sputnik, there have been 42,000, almost 43,000 objects added to the satellite catalog. Of those, 18,489 as of yesterday are still in orbit. And those divide up into what I call whole bits. That's the first kind, the littering. That's almost 8,000. And 10,000 broken bits, the accidents. And there's a very fine breakdown there of the different kinds of things that are orbiting the Earth. And the fact that if you divide it by country, Russia and America are, as you might expect, the main culprits. And China is, for the fact that China's had a lot less space activity over the years, is really caught up on the space junk stage. So how do we fix this problem? So I'm going to go through each of these categories one by one and go, well, all right, what's the solution? Because each of them is different. So the dead satellites. Here's a dead satellite. This one got lucky. They launched it. There was an electrical problem. It died. It wouldn't boot up. We've all had that happen to our new toys, right? But this one was lucky because an astronaut came up and rewired it and fixed it. But mostly they don't do that. But what you should do in general is while your satellite, well, the first thing is, back in the 1970s, they didn't have any way to fix this because most satellites did not have their own rocket engines. Sputnik, when Sputnik was in orbit, they couldn't change its orbit. It was just going to orbit the way that nature made it, with friction with the atmosphere and so on. Nowadays, most big satellites have their own rocket engines to precisely control their orbit, to do various fancy things, and so they can use a little bit of that rocket fuel at the end of their missions to lower their orbits and either get them out of orbit entirely, or at least every bit you lower it means it spends less time in orbit, because the lower it is, the denser the atmosphere, the quicker it'll re-enter. And that'll reduce the probability that the less time you spend being space junk, the less chance there is that you'll hit somebody. High orbit satellites, like in geostationary, like so you move them to a higher orbit, you don't have enough fuel to bring them back. Rocket stages, well, that's also obvious. So again, in the old days, rocket stages, once they'd launched the satellite, usually you could only fire the rocket engine once. And so it had launched the satellite, and then it was done. It couldn't do anything else. For a bit more money, you can design a restartable rocket engine. This isn't as easy as it sounds. You have a rocket, the restart is okay, but getting the fuel to it is not, because you have fuel in the fuel tank that you want to get into the rocket engine, but now the fuel tank is half empty, and you're in orbit, you're falling, you're floating, and so the fuel likes to float into the middle of the tank. It doesn't want to, you don't have gravity to help it go down to the rocket engine. So the way you do that is you have another smaller rocket that accelerates the rocket stage to get the fuel to the bottom of the rocket tank. And so, you know, these kind of, it's a real problem. But so you spend a bit more money, and you make the rocket engine restartable, and you bring it down in the ocean, hopefully at the end of the first orbit, as soon as you've gotten rid of your cargo. The other thing you can do, hopefully someday, is bring the rocket stage back and use it again. Many of you know that Elon Musk of SpaceX has been bringing back the lower stages of his space rockets. Those don't go into orbit, though. The upper stages that go into orbit are a harder problem. But in a few years, they'll be doing that too. So here's a typical satellite payload. It has a rocket stage and a pair of satellites. And the top satellite sits on top of this little box, and the lower satellite sits inside it, because if you just put one satellite on top of the other, the lower one will get crushed. And so this thing gets into orbit, and the top satellite pops off, and the adapter pops off, and the lower satellite pops off. So you end up with 2 satellites, but a total of 4 objects in orbit. And so already for smaller things that we used to eject, we now put them on hinges instead of ejecting them. I think, you know, you could redesign this to sort of split open on hinges and stay attached to the rocket stage, and that would be one less piece of space junk, and then make the rocket stage have enough extra fuel to get it back down again. So you could get rid of those 2 extra pieces of space junk with, again, extra money. Lowers the profits, right? But you have to do it by regulation to convince people that it's important not to have the space junk. I think once commercial companies start losing more of their satellites due to collisions, you'll get to a tipping point where they get much more serious about this. This little chap, it's about yay big, is called a SOZ. Systema Obyczajne Zapustki, I think, and something like that. My Russian isn't good. And there were 2 of these little motors on each of the old Russian Proton satellites. And these are these ullage motors that are the things that fire to force the fuel back in the big rocket stage. And then they get jettisoned to space junk. And then they sit in orbit for 10 years. And then they go bang. With their remaining rocket fuel. So, in fact, one of those, the satellite catalog just cataloged 12 new pieces of space debris yesterday from one of these things that was launched in 2010 that just blew up. You know, that's an obvious solution is you pay a bit more money, you have a system that gets rid of the leftover fuel, vents it into space during the mission rather than just leave it there. And there's been like 40 of these things that have blown up so far, made a lot of space debris. So there's a series of weather satellites that were built by RCA in the 70s and 80s, and they have batteries that seem to really like to blow up after some years in orbit. So batteries have a lot of energy in them. If you don't vent the battery fluids at the end of the mission, it turns out that they can, well, we've heard about like these lithium batteries on planes that have had some issues, and this is a similar issue. Then the Soviets had a habit of putting self-destruct systems on their satellites. They really, really didn't want their stuff falling into American hands. And so they would, if they thought that a satellite was going to re-enter in the wrong place, they would blow it up. This particular series of early warning satellites had an issue that the self-destruct device liked to go, after the satellite had been retired successfully, liked to go off on its own. After some number of years, again, these things were orbiting Earth and then suddenly bang. And so that's just not a good idea. Don't put self-destruct devices on. And then the thing that's really not a good idea is anti-satellite weapons. At the top right, we have a Soviet system from the 60s, which would approach another satellite in orbit and release a whole bunch of like shotgun pellets that would, with high explosive, that would shred the other satellite to pieces. And then on the left here is a U.S. Air Force F-15 with a big missile underneath it that goes into space and just hits a satellite. There was a U.S. Navy astronomy satellite called P-78-1 that was happily taking data on the solar wind and the sun, and then suddenly their data stream stopped because the Air Force had decided to use it as a target. This is the less pleasant way to discover your mission extension has not been approved. That was 1985. All the debris from that has now re-entered, but it took quite a few years for it all to come down. And then we have the collisions, the satellite collisions, and as I explained earlier, the only way to avoid that Kessler syndrome is basically to clean up the rest of the junk, not have as many things in orbit. There's one other thing you can do for operational satellites is you can tell them, you can have them maneuver out of the way if you know that the collision is about to happen. That requires you to be able to predict the orbits very accurately so you don't get too many false positives. Otherwise you're dodging all the time and you use up all your fuel. And so we're making improvements on that, but it's, I think, still the major solution to this has got to be just cut down the amount of debris. So I didn't want to end on such a depressing note on how everything's terrible in space, and so I just want to remind you that there's some really promising developments happening, and here's some pictures of the SpaceX Falcon 9 with its reusability, both in terms of the first stage of the rocket and the cargo ship that goes to the space station, which is also being reused on multiple missions. And so that's a step forward. You know, SpaceX has great ambitions. This is the plan Elon Musk just released for a Mars city with a fully reusable rocket called the BFR. So, yeah, that big something rocket. Even the traditional aerospace companies are being much more imaginative now. This is a recent, again, last month study of a Mars orbit base with reusable Mars surface-to-Mars orbit spaceships. And this is built out of, apart from the reusable spaceships, it's built out of technology that exists today for the space station, sort of put together in different ways. And so, you know, there are a lot of exciting things to do in space. And so if we don't, this is the all this debris from the Iridium Cosmos collision, and just sort of how long it takes to go around the Earth versus how high it is. So we don't want that. We want this. And so hopefully the rules of the road that space agencies are informally developing that go, okay, try and get all your satellites down after 25 years. Don't litter a geostationary orbit. Don't do anti-satellite weapons tests. We'll start to clear up the space debris problem. But as you saw from that graph with the jump where the two bad events happened, it only takes a couple of bad things to make the debris problem much worse. So it's going to continue to be a challenge, and let's just hope that we can clean our act up in space as well as on Earth, and be able to use both in the future for productive things. Thanks a lot.
Terrific. You saw there Jonathan making enormous use of his obsessive database and why it's worth him doing it. Excellent. Please, some questions. Let's see. At the back at the end there.
Two questions. One, can a collision happen so strong that it makes pieces go to escape velocity? And then the second question, what's out at the moon? And your picture of the distance away, you had items out at the moon.
I did, didn't I? Yeah, okay. First question. If you bang each other hard enough, can you get to escape velocity? Yeah, absolutely. In principle, you can. Typically not for most of the actual collisions that happen in practice. You get to apogees, like most of the collisions are going to happen in low orbit over the North and South Pole because that's where all the orbits intersect, right? And those tend to be at velocities where the highest result you get is maybe a few thousand kilometers. It doesn't get to escape velocity. But if you had a bad collision in geostationary orbit, where you're high out of the gravity well and it doesn't take as much energy to escape, you can well imagine that that might happen. The second part of the question was...
What was near the moon?
What was near the moon? Well, there are some probes near the moon. We have a number of, a lot of rocket stages that got our moon probes to where they now are. There are some objects orbiting the moon. And so, yeah, there's a bunch of stuff. And that was a log scale. So on that scale, the moon and halfway to the moon are pretty close. And so Chandra, for example, is a quarter of the way to the moon. So there's a few spacecraft beyond geostationary orbit. Not many, but they're mostly scientific ones exploring the outer magnetosphere. Geotail, the Japanese satellite that's been up there since 1992, bumming around in the measuring the magnetic field out there.
Okay. Yes,
yes. How do you know when stuff has come down? I mean, how are you able to track it?
Okay. So the main, and of course I don't do it personally, right? The Air Force does most of the work. There's the main way people know, right, is you know that something's in a low orbit. It's going to come down soon. You can model the prediction, and then the next time round, your radars don't see it anymore. And then sometimes you get lucky. 3 days ago, there was a re-entry so there was the Russians sent a cargo ship to the space station, and of course that put a rocket stage in orbit as well. It stayed up for about 3 days, and then it re-entered. And the folks in Dubai got a really nice light show and thought they were being attacked by aliens or something. And so you do get reports of space debris. Not a lot of space debris reaches the ground, but quite often you get reports of things that look like meteor showers, but a bit different. And they're slower than meteors, so you can kind of tell the differences. So you go, okay, that's space debris re-entering, and then you can kind of match it to what isn't up there anymore.
We had a question at the front here.
Okay, so with the sprites, which are now the smallest satellites, how bad are those going to be for space junk? Because they're so small and there's so many of them.
Right, I didn't mention the sprites. Good, yeah. So I talked about the CubeSats, which are 4 pounds. The sprites are like a few grams.
Credit card size.
Credit card size, yeah, and they're awesome. They're a great invention. But if you launch a lot of them, you might worry that they're very hard to track, so you won't know where they are. So I wouldn't be very happy deploying 1,000 sprites in sort of medium-high Earth orbit. But the plan so far, what Zach has done and some of it is to deploy them at below space station altitude, where they'll only stay up for a few weeks. I think anything that's below the space station doesn't stay up very long, and so that's not a big littering problem.
More questions? Yes.
Yeah, like, what does one of those little satellites do all the time for a week?
The ones that we're talking about are actually they were done on a Kickstarter thing to have your own like bleeping signal with your and they weren't really doing a lot of science yet. But then when the first CubeSats were launched, they didn't do very much, and now they're doing Earth imaging and communications and things like that. You could imagine a scenario in which even short-lived satellites, if you keep replacing them, right, could provide a useful service. So there are a few things that can be done.
Do you have any questions up in the balcony? Yes.
You mentioned some of the space debris. I think it was an active satellite that was going the west.
Yes. Oh, right. Let me see if I can find that. I meant to test you on that one. Let's see. Bear with me a second here.
Wow.
Yes, you're talking about these little light blue ones here.
There was even on the previous slide there was some right at the top at 180.
I think that might be a mistake. Let's see. Oh, there is one. Yes. Okay, that's the 10,000 kilometers. That's the science satellite cluster, I think. No, 180. Not sure. I'll have to check that one.
Cannot be an error in the database. Yes, it can. Of course.
Yeah, well, it could be, but I don't think so. I think it's one of the magnetosphere satellites, but I'm not sure which. But the ones that I mostly see are, and the fact that it's not in this one worries me, because it suggests that it may be the older data set. So here you have these light blue ones that are going west. So the one country that regularly launches to the west instead of the east is Israel. Because if Israel launches to the east, it starts a war. And so they take the penalty of having to use a bigger rocket for the same satellite, just for good reasons.
More questions? Yes, back to.
Are there any international organizations attempting to address this?
So, right, are there international organizations attempting to address the space junk problem? So, the United Nations Committee for the Peaceful Uses of Outer Space, COPUOS, has meetings about this regularly. And in particular, one of the most effective groups is called the Interagency Debris Committee, or IADC, which is basically a committee that meets now and again of the space junk experts from NASA, European Space Agency, Roscosmos, and so on. And so, yeah, they do all go together and go, hey guys, what are we going to, how are we going to address this? And they've come up with guidelines that are followed more or less, even though it's not an actual law. So, there have been improvements. And, the Chinese were slow to pick up on these, but they seem to be doing more of it now. I think that there is movement. But as usual in these things, right, it's sort of, too slow and too little, but it is at least having some effect.
We have a question right up in the balcony there. Yes.
Hi. Didn't Japan recently try to scoop up space junk?
The Japanese experiment that I think you're referring to, called KITE, was on one of its cargo ships. After the mission, they were going to use a tether. So what happens is, if you deploy a wire with a weight on the end that's about like a mile long or something, then the center of gravity of your spacecraft has sort of changed location where its orbit is. If you then let the thing on the end go, it's going to zip up to a higher orbit, and your other thing is you're suddenly at the wrong orbit, the wrong height for your speed, and so you fall out of orbit. You end up in an orbit with a negative low point. So that was the experiment that they were doing. So it's a cheap way to deorbit yourself without using rocket fuel. So that's one of many, and I will say, in the past year, there have been maybe half a dozen, no, actually maybe like more than that, there's dozens of experiments launched with different approaches to how to get small satellites out of orbit. One of the things, the CubeSat will deploy a little parachute that will slow it down in orbit and make it re-enter more quickly, that kind of thing. So there's a lot of work going ahead on this. It just hasn't reached operational status yet.
I had a question. When you launch the astronauts going up to the space station, this debris, they must go through this? Or
right. And so the trick is, if you're counting down for launch and you're sitting in your seat, waiting to get boosted up into space, the folks in mission control are doing calculations to go, when's the next piece of space debris going over? Is it going to intersect? And sometimes they go, okay, folks, we're having a 5-minute hold to wait until this piece of space debris goes over. So they actually do sort of air traffic control to do that. Now and again in the space station, they have a warning like, oh, we're going to have to boost the space station's orbit to avoid a piece of debris. Or if they get the warning too late, everybody run into the Soyuz and close the hatches just in case we get hold. So it's an operational concern. Sometimes you say, oh, we can't go today because there was a space debris collision warning, so have to reschedule for tomorrow or something like that. So it's at the level of an annoyance now, but you can imagine again if it were 100 times more, you wouldn't be able to go at all.
We have time for just a couple more questions. The gentleman back there, do you have a question? You did have, yeah.
I take it that a CubeSat intersecting the space station in the wrong way would be very disastrous. Is there some procedure so when they release these CubeSats, they keep them out of the way of the space station for their whole orbit?
Right, exactly. So one of the ways that they launch these CubeSats is that a rocket launch is kind of a rough ride. So if you wrap your CubeSat in bubble wrap and give it to a company that's delivering cargo to the space station, bring it up in carrier bags, then they go into the Japanese space station module, load it into a little spring-loaded launcher, and take it out the airlock with the robot arm, and go ba-doing and put out these. And they've launched a few hundred CubeSats this way. And what they do is they make sure that the arm is pointing backwards relative to the direction of motion, so that the CubeSat ends up in an orbit with a slightly lower velocity than the space station, which means it goes and it ends up going down and it never catches up. Then atmospheric drag is enough to make sure it never intersects with the space station. So they do worry about this.
And we had one more question at the front. No? Okay.
How was the altitude for Chandra chosen, and are the other space telescopes at the same altitude?
No, so really, to be honest, as far as I can tell, these things go in fashions. Until the 1990s, the fashion for space telescopes was that you went in low Earth orbit, like the Hubble, particularly in the days when we thought it would be cheap to repair them with the space shuttle. Then by the time Chandra came along, we knew that wasn't quite the case. We wanted to be far from the Earth so that you could have, in a long orbit, you can have long uninterrupted observations. And also if you're very high, the radiation belts, you're not going through the radiation belts as much. And so you can have long uninterrupted observations with no background. And that was, with no interference with radiation, that was popular for a few years. The European XMM Newton, our sibling, is in a very similar orbit. And then someone realized, actually, it takes very little more energy to get to a solar orbit. And then you don't go in the radiation belts at all, and there's some other advantages. So they put Spitzer, the infrared telescope, in solar orbit. But that has a disadvantage, which is that you end up very far from the Earth and it's hard to communicate with spacecraft. Spitzer was only meant to last a few years, so they didn't think it would be a problem, but they're still going, so it is. So then they went, no, the real place for astronomy telescopes to be is Sun-Earth L2, the second Lagrange point, 1,000,000 miles towards midnight. And so if you take the Sun and the Earth in a straight line and keep on going, 1,000,000 extra miles, so 94 million miles from the Sun, as you orbit the Sun, you want to orbit slower than the Earth, but the Earth is tugging on you, so it actually pulls you along, and you keep in the Sun, you keep in the same line. And that's a stable point, or semi-stable point, and so now that's where almost all the astronomy missions are going, and it means you have the Sun and the Earth behind you, so in front of you is always really dark and cool, and so you put your solar panels and sunshade on one side and look out the other way, and that seems to be currently still the best idea for where to put your astronomy satellites. That's where James Webb is going, that's where Gaia is, that's where Herschel and Planck were, and so a new fashion may come along at some point, but right now, that's where I would buy your real estate.
Okay, I'm afraid that's all we've got time for. Let's thank Jonathan again.
Okay, guide for the month for August 2022. Obviously not the most popular time for astronomy. Right now. No questions for that side of the room, thanks. Okay, so things to watch for in August, September. Our next meeting. Full moon was a super moon, and that was the 12th of the 8th, a few nights ago now. And the new moon occurred on the 27th of the 8th. Hopefully we get a little bit of clear slide between now and then. A couple of things to watch for. Mercury at the moment is a very good spot for those who want to observe it. It's heading towards its greatest elongation east on the 28th of the 8th, about 27 degrees away from the sun, so it should be fairly high in the evening sky, and actually it's black sky, so you should be able to find it quite easily. On the 17th, which is tonight, which is approximately Buckley to see, it's about half a degree northwest of an irregular cluster in Leo. So it would have been a nice little photo op with the cluster and the planet. The galaxy and the planet. 1958, the last quarter moon. Comet-wise, keen stars, the only one around at the moment. It's about 6 magnitude, so quite bright for a comet. And it's pretty much hanging around Scorpius for the whole month. I think everything's been playing right. On the 23rd, about a bump west of Beta Scorpius, and down the bottom, I thought it was another one there, Ceres, 5 degrees north of Venus. The reason I put that in there, Ceres obviously is the brightest of the asteroids and fairly close to Venus, so hopefully make it fairly easy for you to find if you want to have a look at it on a telescope. As I said, Mercury goes to elongation on the 28th of the 8th, and probably hang around there until about the end of the month, after which it'll start to head to, or sorry, early September, after which it'll start to head towards the Sun, to go towards inferior conjunction. 4th of the 9th we have first quarter moon, and on the 8th of the 9th the moon is at perigee. And you'll notice a slight difference there between full moon, which occurs 2 nights later. So it's not a super moon next month. This is out by 2 days. Jupiter is about 1.5 degrees north of the moon. I did put the time there, 1 AM. So if you want to hang around until 1 AM, not too late. You can have a look at Jupiter and the moon. And on the 17th of the 9th, Neptune's in opposition. So best point to observe Neptune if you have the hankering to see a blue dot. So the sky now, obviously sort of rotates a little bit each month, and main points are still up the top there, you've got your lagoon and Trifid nebulas, up around the T-top there, which is actually Sagittarius, centre of Sagittarius. That's where the galactic centre is, so there's a lot up there. Pluto's up in there somewhere too, so if you can pick it, good luck. Other things, your Tarantula Nebula, Anita Carina, fairly low on the horizon, or southern horizon at the moment. Should still be observable, might have to wait until a bit later in the night for the whole thing to rotate just a bit more. And obviously the two clusters, 47 Tucanae and Anita Centauri, are actually quite good observing positions at the moment, because they're sort of out like that, out like that, too high or too low. Looking to the north, there is actually the Perseus meteor shower occurring at the moment. Perseus is down about, or Perseus is down around here somewhere, so the radial for that is below the horizon. I think you might still see some. In actual fact, on the news the other night, did you see that one in daylight in America? They were standing in their backyard and one actually came through, a sonic boom was a bit overhead. And a woman standing there at her boat, what the hell was that? And someone had actually filmed. Apparently that is the Perseus. They're about 150 an hour at their maximum point. And quite large, very consistent shower, but tends to be a little bit more favouring in the north. Okay, so the planets, as I said, Mercury moving towards its maximum elongation to the east, which means it's an evening object at the moment. We're starting to get quite a few of the planets heading into the evening sky, so something to look at for the upcoming Scout and Cup groups and public nights if you get to these skies. Very good position until early September, so it's going to be hanging around a reasonable distance above the western horizon. And later in September it moves into inferior conjunction, meaning it's between us and the Sun. Venus, still a morning object. It's a little bit lower in the eastern sky now, getting lower as it moves to what is known as superior conjunction, in other words on the other sun relative to us. Give it a month or two and then it's going to pop back into the evening sky for us to view again, so probably around about October, November. Earth, days are getting longer. Obviously we had the spring equinox on the 23rd of the 9th. And hopefully a bit of warm and clearer weather with it. The major planets, Mars is rising just after midnight, so it's on its way. I think opposition's in October, November, and so hopefully it'll make its reappearance in the evening sky in the next few months. On the 27th of the 8th, it's at its western quadrature, which means it forms a 90-degree angle between the Earth, Sun and Mars. And the advantage of that apparently is because it's virtually the side on as it will get, it's about 84% gibbous. So you will see a slight dark side to it, and 84% of it is actually lit. And that's just something. Saturn's the other one, and it's quadrature, when you get the best shadow on the rings of the planet. Jupiter, air rising before midnight, so it's just before midnight, following Saturn. So we've got Saturn and Jupiter coming up now. Couldn't be more. All these beginners who obviously got worn out on Eden's cosmology course. But obviously a fairly easy planet to find because of relative brightness and line, and certainly got plenty of stuff to look at with its band, its red spot, and its four big moons. Saturn, as we're all aware, the public night earlier, Saturn is a very good spot for view at the moment. It's very good for public lights if we can get clear sky once again. Saturn was at opposition on the 15th of this month, so that basically means it's directly north of us at midnight. Okay, so and probably being, well, it means up until midnight, it's in the eastern half of the sky. Good for viewing. Uranus, found in Aries. Found in Aries in 2025 apparently. Fairly close to Mars early in the month, but then it will start to drift. And it starts to take a retrograde motion. So it appears to move west against the sky background. It's just a vagary of our orbit, or relative orbits, that all the outer planets at certain points in their orbit tend to go the wrong way, or appear to go the wrong way. Neptune rising about 8 p.m. And as I said, we'll be playing right at each opposition. You're not going to see much more of a blue dot in the roof of the side telescope. Although it gives me D80 and I got a blue dot picture, so hopefully my 10-inch dot goes a little bit better. Not a lot of stuff to look at with Neptune and Uranus, purely because of the distance away and the fact that they don't have a lot of stuff to look at. Here to the planets, Mercury there, and obviously, imagine the Sun there, Mercury just slightly the other side of it as it comes around, so we're getting more of its space turned towards the Sun here. This is the 5th of August, so past that. This is about where it is now, and then on the 28th, when there's a massive elongation, we should see about half the planet. Okay, so you get the same figures you do with the different phases. Venus, you'll have the shadows on the other side. And what's happened here with Venus now is it has actually gone around past the Sun, from where we are. It's still pretty bright, purely because of the reflectivity, but where it is, we're seeing a lot more face, a little bit smaller. Mars, you'll note, getting a lot bigger. And that's because Mars, well, it's not actually coming towards us, we're actually catching it. So it's trying to get your idea of what's going on. It's there, and we're coming around up here. Saturn and Jupiter the same sort of things. Saturn still got things tilted towards us, although they are closing. And because they are usually about every month in 2025, we will pass through the ring plane. So if you really want a unique look at Saturn, you'll see the planet with no rings. It's got a really good telescope, you can see it there dot. And Jupiter, Jupiter's always spectacular, whether you got to get up in the morning or the evening to see it. It's just got so many features. The reason it's so big now is we are on the same side of the Sun as it. So it'll now head towards opposition, which is towards the end of next month. So that's why we're seeing it fairly sizable, because it's 4.5 astronomical units from the Sun. We're 1 astronomical unit. So at the moment, the difference between us and it is about 3.5 astronomical units. But when it's around the other side of the Sun, it's actually further, so it's smaller. Not that you really notice, it's a pretty good object anyway. And Uranus, Neptune. Uranus is at 5.7 magnitude, so kids' eyes could probably see it on a really dark night. Older people, no hope. And get you to make 7.8 magnitude, so definitely telescope objects. Other stuff, comet pan-stars is expected to be 6 magnitude during August. The beauty is it's a evening object. So basically all evening, setting around midnight towards the end of the month. Currently in Scorpio, and it hangs around Scorpio, the head of Scorpio, towards the end of the month there. And apparently going to have some close conjunctions with Antares and the other brighter stars in the head of Scorpio. So the astrophotographers, if you want to find a comet and photograph it through a telescope, it's probably the easiest spot of the sky to find it now. Yeah, so that's during September, which we cover a little bit of September here for next week. And as I said, with the meteor shower, 17th to the 7th, 24th to the 8th is the Perseids. We're past the maximum, which is 12, and I think that's when the sonic boom one was shown on the TV. So there's a fair few there. It's a little hard to see in the southern hemisphere because it's gradient of figures below the horizon. So we've sort of got to hope to shoot up and over. Nice information provided by Astronomy 2022, well scores in Northfield. You still got some of them for sale? Yeah. I think most of the people here have probably bought them. Any questions? Thank you. I'll wear the suit next time.
For quite a long time, the sort of adopted, agreed definition for the edge of space has been something called the Kármán line, which is located at 100 kilometers above the Earth's surface. It is not a legal definition, but it's a definition that's been adopted by the Fédération Internationale Aéronautique, which is the World Air Sports Federation. But it's a largely unsatisfying definition because, of course, the atmosphere doesn't have an edge. It's a continuous fluid body. It has lots of different properties in lots of different regions, but none of them have rigidly defined edges. And in fact, the properties change as a function of time and solar activity and lots of other things.
100 seems almost too perfect, doesn't it?
It does. So recently, a paper's been published called The Edge of Space, Revisiting the Kármán Line. And this was work done by an astrophysicist named Jonathan McDowell at the Harvard-Smithsonian Centre for Astrophysics. And he takes a closer look into whether there is a real scientific definition for the Kármán line. The original Kármán line definition was roughly associated with the idea that there's a boundary between where aeronautical forces stop and you no longer get lift from the atmosphere. Aeronautical lift is a mechanical force. It's generated by contact with a fluid, the fluid obviously being the atmosphere. And if you run out of fluid, you run out of force. And so at the Kármán line, you're sort of where an aircraft would have to travel at a speed that's greater than the orbital velocity in order to get enough lift from its wings to stay in the air. So in this paper, we looked at the orbits of 43,000 satellites that have been tracked over the years. And of course, most of them are way above the Kármán line. But there were substantial numbers that throughout their orbit would pass below the 100-kilometer line, getting even closer to 80 kilometers. And not just on their last orbit before they disintegrated, but they had multiple passages this low. And so right away you can say, okay, well, the 100-kilometer line doesn't make a lot of sense. You can't have a satellite in orbit and then it comes in and, oh, for a little bit it's not in space, and then it goes back into space and on and on and on. And so right there is some evidence to at least support the idea of revisiting this definition. And so the second thing he did was actually use an atmospheric model and actually make the calculations of, for a typical satellite, where would the drag forces be enough to sort of cause it to fall back to Earth.
Sort of like the death zone for satellites.
The death zone for satellites, that's exactly it. So the conclusion he makes is that for a typical kind of space vehicle, the gravity will exceed the aerodynamic forces for any object in steady flight at that altitude lies in about the 70 to 90 kilometer range. So he factors in the time variation and all of this stuff and finds a range for this limit, but notes that it's always well below that 100-kilometer line. This is just one argument. Other arguments would look at the structure of the atmosphere, which is quite complicated, but again, it's divided into specific layers, mostly based on where the gradient in temperature changes. These are called pauses. And so at about 85 kilometers, we've got the mesopause, which is the boundary between the mesosphere and the thermosphere. And that marks the point which is the coldest point in the atmosphere. Below that point, the chemical composition of the atmosphere is mostly steady. And above that, you've got different molecules moving in different ways. And so from atmospheric physics, there's also a boundary more towards the 80-kilometer line. So what's really interesting about this argument is to actually appreciate how close space is. Because 80 kilometers, 100 kilometers, that's not that far away. You can easily drive that in an hour. So I thought it might be fun to look on a map and actually appreciate, to scale, how far away space is. Of course, our map is centered on the center of the universe, which is here in Nottingham. And the unit that we're going to use to mark scale on this map is the humble Lego block. The height of this brick is 3.2 millimeters. And so I've printed this map so that 5 of these Lego bricks represent 100 kilometers on this map. To put some things into scale, first let's talk about airliners. So when we're on a commercial airliner, we're traveling at about an altitude of 10 to 12 kilometers. So when we're traveling on a commercial airline, we're not even traveling at the height of this brick above this map. So the next scale I'm going to show you is the world record for how high a human being has jumped out of a balloon to skydive down to Earth. So this record was broken recently by Alan Eustace, and he jumped from a height of 41 kilometers. So that would represent 2 bricks on this map. And so now we want to go up to the Kármán line. And so the debate we're discussing today is whether we define the edge of space at 80 kilometers, which is here, or 100 kilometers, which is here.
Doesn't seem that high anyway, does it?
So I think that's the amazing thing to appreciate. So if this height is 100 kilometers, what's really amazing is how small this number actually is, how close we are to space. So if I tip this on the edge and I've got a 100-kilometer marker here, you can see that Nottingham is closer to space than it is to London. And I can get to London in an hour and a half on the train. All right, so maybe Nottingham to London doesn't mean very much to you. But if you're in New York, you're closer to space than you are to Philadelphia. If you're in Los Angeles, you're closer to space than you are to San Diego. Oh, let me do a Canadian one.
Okay.
If you're in Montreal, you're closer to space than you are to Ottawa.
I got no idea where those places are. All right, cool.
I looked up Adelaide for you, but nothing's near Adelaide, so it didn't work.
When do you become an astronaut?
So NASA gives its astronaut wings to anyone who's trained and flown a successful mission that reaches above 50 miles, which is 80 kilometers. So that's actually the lower limit. And there's a similar acknowledgement from the US FAA for civilians who have piloted a successful flight above that line.
Is this important? Like, is this just a bunch of people writing papers, or does it matter where space starts and finishes?
So it matters from a scientific perspective because scientists like to study these sorts of things. So it's perfectly understandable that people who are interested in atmospheric physics and the orbits of satellites would care. But it actually does have some wider issues that now touch on issues of economics and politics and defense and things like that. So I mentioned there is no international agreed legal definition of space. There have been for some time moves to make a legal definition, but that's always been opposed by the US. And you can understand why, because from a military point of view, a government wouldn't want to be restricted by international space treaties when it's trying to launch high altitude ballistic missiles, something like that.
And what about space tourism? I guess they want it to be as low as possible so they can sell their space flights.
Well, that's the other issue. So commercial space tourism is becoming a thing now. As we film this, Virgin Galactic has just managed to pilot a vehicle to 82 kilometers. By the NASA definition, that counts as entering space. By the FAI definition, it doesn't, because they haven't reached the Kármán line. But it would matter very, very much to a commercial enterprise to be able to say that they can take people into space. Now, practically speaking, you know, I think what you would want from a space mission is the experience of weightlessness and the experience of looking out the window and seeing the Earth as a ball. You would get that from 80 kilometers as well as you would from 100 kilometers.
But like, I look at that and I look at how low that is, and I imagine, God, how come you can see the curvature of the Earth from such a... That doesn't seem that high.
I think partly that's because I've printed a map out on a flat piece of paper. So in reality, this is a curved surface that I'm showing you here. You might not see it as a complete ball, but you would definitely see the curvature of the Earth. You would experience the Earth as a sphere. It becomes quite clear that for a commercial enterprise, you're not going to want to waste money and fuel and increase risk by taking people up to 100 kilometers if they can get the same experience going to 80 kilometers. But part of that experience for people will be being able to say, I have officially been to space.
Where would you be drawing the line?
Well, I'm pretty convinced by this paper. I mean, it has some pretty sound arguments from a number of different directions. So I think if there was a move to redefine the 80-kilometer line as the McDowell line, I think that should go down very well.
But McDowell says 70 to 90. That's like super vague.
Well, that's just because scientists, you know scientists, you've talked to enough of us over the years, and we like our error bars and we like our confidence intervals. But if you want to define a line, you might as well put it in the middle of a region that is well bounded. This paper has revisited the numbers, and the back of the envelope calculations that gave 100 are now refined, and they might not give a more precise number, but they at least show us that it's not 100. And so it's very unsatisfying to keep it at that level. I thought it would be fun to actually build up a perspective on the altitude that other objects in space get to. Part of this was motivated by the fact that just last week I went outside as I was coming home from work and happened to see the International Space Station go overhead. It was really bright, it was a beautiful passage, and as always I was struck by looking up and thinking, oh my God, there's human beings flying above my head in orbit around the Earth. That's pretty amazing. How far away are they actually up there? The space shuttle, now no longer in existence, but I couldn't resist getting my Lego out, used to take astronauts up to the International Space Station, like Mae Jemison, and that's at 400 kilometers above the surface of the Earth. So in our Lego bricks, if this is 100, we'd need 4 times that amount. So let's do this. 13, 14, 16. I feel like I'm on Lego Masters. 20. Excellent. Right, so this is the orbit at which human beings continuously inhabit a space station orbiting the Earth. And even that is not that high.
I'm slightly less impressed. That wasn't your goal, was it?
I think one of the values of human space flight, one of the real values, is cultural, not scientific. And it's putting human beings high enough to give them that perspective on space. And if they only have to go that high to be able to look out in one direction and see nothing but the infinity of space, and then turn around and look down and see the Earth in enough scope to see not borders and not resources to be exploited, but to appreciate that this is the one and only place where life in the universe exists, and to look out to the horizon and appreciate how razor thin that precious atmosphere that keeps us safe is, then I think it's quite amazing that you don't have to get that high up to find a perspective where you realize just how precarious and how delicate the ecosystem and the geosystem on Earth is.
What else do you want to show me? You got Hubble there, or?
Okay, so I've got Nancy Roman and the Hubble Space Telescope, one of my favorites. And this orbits at an altitude of 540 kilometers. It used to be higher, but it's slowly, even at that altitude, it suffers from cumulative atmospheric drag over time, so it's going lower and lower. And that represents pretty much the highest altitude that the space shuttle could reach, because Hubble was designed to be put into Earth orbit at an altitude where the space shuttle could repeatedly go and service it. And it's a good thing it did, because we benefited from those servicing missions quite a lot. And so I've got 20 bricks now, and I need to put 8 more to get up to the height of the Hubble Space Telescope. So 1, 2, 3, 5. Now we've run out of thin bricks, so we're going to put 3 more on top. And so that's how high the Hubble Space Telescope is. All right, so there's the Hubble Space Telescope. Yeah, there you go. Success. Not to scale, of course. The Hubble Space Telescope is about the size of the bus, not about the width of the United Kingdom.
What's higher than that?
Well, there's lots of satellites up there in orbit. GPS, Global Positioning Satellites, orbit at an altitude of 20,000 kilometers above the surface of the Earth. That would require 1,000 Lego bricks, and I'm not going to build that today. But I would just note that that would take us 3.2 meters above this map.
Okay.
So right through the ceiling.
Up there somewhere.
Okay, and these are satellites, they're in geosynchronous orbits, so they orbit the Earth twice a day. But there are satellites that are even further up. They're called geostationary orbits. Their orbital period is matched with the rotation of the Earth, so they orbit once a day, which means that they are effectively always above the same location, above the equator. And these are the satellites that give us our weather readings and act as our communications relays. On this scale, you'd need 1,789 bricks, which would take you 5.7 meters above the table.
All right, well, that's way up, way up. We're looking here down at the UK and Europe. How many bricks down is the other side of the Earth?
So I said that the GPS satellites are at 1,000 bricks above the Earth. But the other side of the Earth would only be 640 bricks, so that's less than the height of the GPS satellites.
What if I wanted to go to the moon?
Of course you want to go to the moon. Well, you would need to travel 19,220 Lego bricks away, which on this scale would be 60 meters. So there's been enough recent attention to this idea that the Kármán line needs to be redefined, that the organizations that deal with aeronautical things and the organization that deals with astronautical things are proposing to get together in the coming year to have a symposium to look at the scientific and the political and whatever other arguments go into this to see if we need to actually have a definition of where is space and what that might be. We made a video a couple years ago saying that Voyager's left the solar system. It just left the solar system again. So most things in space don't have a hard edge. And that means that different definitions can apply, and you can argue till the cows come home about whether Pluto's a planet, or where the solar system ends, or how big is the Milky Way. And to some extent, you will never get a satisfying answer, because science often comes with caveats that say it depends what you mean.
Who doesn't like birthday cake? And what I'm going to show you today is that there are good ways and there are bad ways of cutting a cake. And the classic way, the bad way, is like this, which would be normal. You put the knife in the center, one bit of a slice, another bit of a slice.
That's like the classic.
It is the classic, isn't it? It's almost like a pie chart. You know one thing about the word pie chart? In France, they call them camembert, which is like a cheese. So it's actually like a cheese chart in France. Interesting cultural differences in maths speak. So this is what you would do. You take this, you would put this over here, you eat it, and then you leave this in the fridge overnight. And the reason why this is a really bad way of cutting a cake is that these bits here are just going to get dry. And so when you come the following day to have your cake, you know, you do another one, you know, another slice like this. This side here, lovely and soft. This will be dry and horrible. You're not maximizing the amount of gastronomic pleasure that you can make from this cake. There is a better way, a way that is more than 100 years old and was discovered or invented by one of Britain's most famous and brilliant mathematical scientists. This is a copy of Nature, the famous science magazine from December the 20th, 1906. And in the letters to the editor here, it says, the headline, "Cutting a Round Cake on Scientific Principles." The ordinary method of cutting out a wedge, he writes, is very faulty. What he suggests is, and he gives an illustration for it, the proper way, the scientific way, the mathematically perfect way of cutting a round cake, and it is as follows. So we have another cake. The first slice will be like this. It's breaking all the rules of cake etiquette. Perfect. Okay, so this is the first one, and then I need to find a way of taking it out. Okay, we can stick that there, and that has got to be the prime. That's the prime steak of that cake, isn't it? It's the T-bone cut. Here, what we need to do, we need to close the cake together like this, and that's going to come apart. So look what I've got here. I have got some rubber bands to make sure that stays together. The following day, all the flesh, the sponge, is going to be nice and soft. So how do we do the second slice? The second slice, I guess it's not your birthday anymore, so you're not going to have one that's quite as big. It'd be interesting to work out the actual proportions. This is, and you get a lovely breaking of the elastic bands too, which is exciting. This is slice 2, or it actually is slice 2, which has 2 slices, 2 parts. Good. So we put this back together, and we can keep on going. Obviously, I'm going to want to use the elastic band to put the cake. So yeah, that is perfect. That is going to stay so fresh for day 3. Day 3. How should we do day 3 again? Let's turn it round. I think this is going to be the slice for day 3. Again, the satisfying snap of the elastic bands. And I don't know if you've thought about it before, but these triangular slices are really annoying anyway, because it's not very satisfying. Having a nice uniform slice like that is a lot better. So here we go again. This is at the end of day 3, there's 4. And this is going to be perfect. And gradually we are slicing it. Keep on going.
We've got a cake. We're going to cut it. Now, if there was 2 of us, as there are, this is quite simple. You just, one person cuts, the other person chooses. It's all nice and fair. No one's envious. Perfect way to cut the cake. A lot trickier though when you have 3 people. We've got 3 people, Alice, Bob and Charlie, and they're going to share this cake, and we want to make sure that it's as fair as possible and that at the end nobody is envious of anybody else's cake. Turns out there's a very good way to do this that's actually quite recently discovered, and I'm going to try and talk you through it. So Alice goes first, and Alice gets to cut the cake into 3 pieces that she feels are equal. So she would be happy with any of those 3 pieces. Oh gosh. Okay, I'm going to go there. Thing is, I've got a get out jail free card because it's a fruit cake, so I can just claim that there's more fruit in one side. Yeah. That was what I was aiming for. It's not bad.
Right.
All right. Okay.
I think I can see the dud piece, but yeah, anyway.
Which one's the dud piece?
I think that's a bit small.
No.
Well, you have
got
that one,
more
then.
sparkly bits on it. Yeah, absolutely. There's more to a cake than just size. Some people like the sort of crusty bit around the outside. Some people like the sugary bits. Some people, hate the fruit. It's your personal preference that comes into this as well. Okay, so Alice has cut the cake into 3 pieces where she wouldn't mind which of those 3 pieces she got. Now it's Bob's turn. So Bob gets to pick which he thinks are his 2 favourite pieces. Now, you there said that one was the rubbish piece. So let's kind of leave that one to one side and assume that Bob goes for one of these 2. But Bob, from those 2, says which he thinks is the best piece of all. And let's imagine that Bob thinks this bit's the best bit. Now what Bob has to do, he gets the knife now, and Bob gets to cut a little trimming off of his favourite piece until his favourite piece is now equally as good as his second favourite piece, right? So that little trimming kind of goes to one side there. So now Bob doesn't mind between getting this one or this one. It's fine. He's happy with either of those. Alice is sort of sitting to one side, desperately waiting for them to hurry up so she can have some cake. Charlie, it's now Charlie's go. Charlie gets to pick which piece of cake he wants to eat. He can have whichever he wants. So Charlie might pick one of the pieces that hasn't been trimmed, or he might pick the piece which has been trimmed. Whatever piece he picks, let's say he picks this one here. It's now going to be Bob's turn to choose a slice of cake. If Charlie didn't take the trimmed piece, Bob's going to want it because he's already said that that's his top, you know, in his top two, joint top. So Bob's going to take that piece. So now Bob's happy. Charlie's definitely happy. They got first choice. Bob's definitely happy because that was his equal top two. And now Alice ends up with this piece, and she's definitely going to be happy too because she cut the cake in the first place and she cut it in a way that she thought that all three pieces were equally fair. So that's fine, right? So that's the majority of the cake sorted. Now we have to deal with this trimming, which looks a bit pathetic.
You can't just toss that though. There's
no
waste.
No, that's wasteful, Brady.
All right.
No, because Charlie went last on the first main cake cutting section. Charlie now gets to go first on this bit. So Charlie gets to cut this trimming into three pieces so that he thinks that each piece is equally as good as the others. Okay, now once he's done that, now Bob gets to pick which of those pieces he wants. Let's say Bob goes for this one here. Now, Bob is definitely happy because he's got his number one choice out of the trimmings, and we already know that he's happy with his main chunk of cake. Now it's Alice's go, and whichever one Alice picks, she's definitely going to be happy because in the very beginning, she thought that all three of the pieces of cake were equally good. She's ended up with one that hadn't been trimmed off, and now she's got an extra bit, so she's definitely going to be happy. And then finally, Charlie ends up with the last little trimming, and he's definitely going to be happy too because he cut the trimmings in a way that he thought that they were all equal. So there you go. That is envy-free, totally fair and totally delicious cake. There is actually an N-person version of this algorithm. The only thing is the number of cuts that it takes to get this sort of envy-free solution gets a bit bonkers.
Yeah, so what do we start getting? Trimmings of trimmings?
Trimmings of trimmings and trimmings of trimmings, trimmings. So in general, the number of cuts that it takes to divide a cake between N people fairly is N to the 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 N. Which is kind of bonkers.
So you can certainly appreciate how slowly Mercury and Venus turn around, you know, and you can see why one day is like the year is getting on for a good fraction of a day, or 2 years equals 1 day in case of one of them. And of course, Uranus is on its side as well, being not right the way over. And also how quickly Jupiter turns, so that as you're observing it through a telescope of an evening, it's, you know, it will turn significantly in a matter of a few hours. Absolutely.
It's amazing most of them are tilted, roughly tilted the same amount.
Yeah.
In the same direction.
Yeah. And with that, we'll close the meeting until next week. So, oh, sorry, until next month. Yeah, thank you.